Welcome to the online series of heat and mass transfer. Today we are going to solve the problems on fins, rectangular and triangular fins. Problem: a body of an electric motor is 360 mm in diameter and 240 mm length. It dissipates 360 watt of heat and its surface temperature should not exceed 55 degrees Celsius. Right? So the given structure is an electric motor and the motor diameter is 360 mm and the length is 240 mm. The motor dissipates 360 watt of heat and the surface temperature of the motor should not exceed 55 degrees Celsius. So on the above surface of the motor, fins are fixed. The fins are longitudinal fins. So longitudinal fins of 50 mm thickness and 40 mm height are proposed. So the heat transfer coefficient is 40 watt per meter square Kelvin, where the ambient temperature is 30 degrees Celsius. Determine the number of fins required if K is equal to 40 watt per meter Kelvin for the material. So given data is the base temperature, the motor base temperature or surface temperature is 55 degrees Celsius and the ambient temperature or atmospheric temperature is 30 degrees Celsius and the heat transfer coefficient is given as 40 watt per meter square Kelvin and similarly thermal conductivity K is given as 40 watt per meter Kelvin. Next, the specification of the electric motor. So the motor having a specification of diameter that is 360 mm, that is 0.36 meter, length is through 240 mm, that is 0.24 meter. And the specification of the longitudinal fins are thickness. So thickness is given as 15 mm, that is 0.015 meter, and the length or height is given as that is 40 mm, which is equal to 0.04 meter, and width is 0.024 meter. So the width is not given. Instead, the fin is covering the whole length of the motor. You can see from here. So the width, this is the width is covering the whole length of the motor. So this is the length and this portion is the thickness and this is the width of the fin. Here to refer the graph, page number 51 in heat and mass transfer data book. So you can refer the page 51 and you can see the fin over here. This is a rectangular and triangular fin. So this is the cross section of the rectangular fin. So now we have to mark the dimensions for the given fin. So you need the length, the thickness of the fin, as well as you should also know the characteristic length. So this is what that is given in the data book. So we're going to calculate these things. That is, first thing is the characteristic length. The corresponding equations are available in the data book. That is, LC is equal to L plus T by 2. So L is the given length of the fin and T is the given thickness of the fin. So we can find the characteristic length. Similarly, we can find the mean area for the rectangular fin. So AM is equal to T into LC. T refers to the thickness and LC refers to the corresponding characteristic length. Similarly, you have to find the surface area. So surface area is twice the length of the characteristic length, that is L suffix C, into depth. Here depth refers to the total width of the fin. So total width, that is the fin is covering the whole length of the motor. So this is the depth, or we call it as a width, that is 0.24, and depth to LC is characteristic length and depth is given width of the fin. So next we have to find the efficiency of the fin. So again from the same given figure, so this is the cross section of the fin. So there are two equations are given. One equation is with respect to x-axis and one equation with respect to y-axis. Why they are given the fin efficiency, whereas in x is given the characteristic length power 0.15 into h into k, that is thermal conductivity, into its mean area. So next step, you are going to find the x-axis, and for the corresponding x-axis we can locate the efficiency from this graph. So first step, you're going to find the x-axis region. So x-axis, the equation given in the x-axis is, that is characteristic length power 1.5 into h, that is heat transfer coefficient, divided by k into its mean area. By substituting the given values, we can find the x-axis as 0.3. So locate the x-axis. So x-axis value is 0.3. So by locating the x-axis, so 0.3 over here, so 0.3 lies between somewhere 0 to and 0.5. So the x-axis is lying here, so this is the x-axis. So you draw a corresponding straight line in order to meet the curve. Draw a straight line in order to meet the curve. So this straight line meets the curve. Now we have to find the corresponding efficiency. So from that point, the point which touches the curve, you draw a straight line so that it makes the y-axis. So this is the efficiency. So the efficiency is meeting in the y-axis. So the fin efficiency is around, that is it may be around 89%, or it will be in numerical it is 0.89. So next we are going to find the heat transfer per fin. So this equation is given in the graph. So you can see from over here, that is Q is equal to neta into A is H into TB minus T infinity. So this is the equation used to find the heat transfer. So Q is equal to neta into H surface area into its del T. By substituting, we can find the heat transfer. Q is equal to 20.29 watts. So they also asked to find the number of fins required. So fins required is equal to total heat transfer, that is Q, divided by heat transfer per fin. So total heat transfer, that is this is the heat transfer due to by the motor. So they are given the given data as, that is heat transfer by the motor was 360 watts. So this is the heat transfer by fin. So the heat transfer per fin was calculated as 20.292, right? By getting the ratio, we can find the number of fins. So number of fins required is 18 fins. So next we are moving to the circumferential rectangular fin. So the problem. So in the problem is given as the circumferential aluminum fin. So the fin is given as circumferential aluminum fin. The aluminum thermal conductivity is 200 watt per meter Kelvin, and it is having a rectangular profile. So the profile of the fin is rectangular, and the specifications are 1.5 centimeter width and 1 centimeter thickness. So the fins are fitted on a 2.5 centimeter diameter tube. So the fin are fitted on a tube. The diameter is given as 2.5. So the fin base temperature is 170 degrees Celsius, and the ambient air temperature is given as 25 degrees Celsius. They asked to find the estimate the heat loss per fin, that is Q. The heat transfer coefficient may be taken as 130. So the given H value. So the given data, the base temperature is given as 170 degree, ambient temperature is given as 25 degrees Celsius, heat transfer coefficient H is given as, that is 130, and K, aluminum material, K is equal to 200 watt. So fin specification, the fin is attached to the radius of the tube, that is diameter of the tube. So first find the radius for it. So R1, diameter is 2.5, we convert into radius. So R1 is equal to 0.0125 meter, and the corresponding thickness, that is thickness of the fin, we call this a length or width. The fin is given as 1.5, in terms of meter is 0.015 meter, and the thickness is 0.01 meter. So again you refer to the concerned data from the heat and mass transfer data book. So you can see the circumferential rectangular fin. So this is the fin. So this is the cross section area of the fin. So you have to locate the parameters. You should know what is R1. You should know the thickness of the fin length of the fin, thickness of the fin, and the outer radius. So this is initial radius R1, and thickness, that is length of the fin, thickness of the fin, and outer radius R2. So next we are going to locate all the parameters required for this rectangular fin. Already I told we need to calculate the characteristic length L. So these equations are available in the corresponding page in the data book. So LC is equal to L plus T by 2. This the L is the length of the fin plus thickness divided by 2. And you are going to find the top radius, that is R2. So R2 is equal to given R1 plus the characteristic length, and mean area is equal to T into that is R2 minus R1, and surface area A is equal to 2 pi into R2 square minus R1 square. So you can get the corresponding characteristic length as 0.02 meter and second radius as 0.325 meter and mean area is 2 into 10 power minus 4 meter square and surface area is 5.652 into 10 power minus 3 meter square. Again, you have to go to the same graph. Now you have to find the efficiency. In order to find the efficiency, you have to locate or you have to find the x-axis, and finding the x-axis you have to mark the corresponding efficiency value. So the x-axis is given as that is LC power 0.15 into H into Ka. So substitute the characteristic length into heat transfer coefficient thermal conductivity K into its mean area, will get the equation of the x-axis. So x-axis value is 0.16. So 0.16 is located somewhere here, and there are several graphs are shown over here. So graph values ranges from 1, 2, 3, 4, 5. So in order to find the graph, there is a expression is given. That is the expression is ratio between the higher radius minus lower radius. So higher radius is R2 and lower radius is R1. So now find the ratio between the radius. So the ratio between the higher radius and lower radius is 2.6. So 2.6 lies somewhere between 2 and 3. So a curve might be lying over between 2 and 3. So already we located the x-axis, isn't it? X-axis is 0.16. Then you make the x-axis to meet at a curve where the curve is 2.6. The curve point is 2.6. So this point is fixed. Then from this point we can make the efficiency by meeting it with the corresponding to the y-axis. So this line meets with the y-axis. So we can find the efficiency as a 0.91, that is 0.91, or simply we can call the efficiency as 91%. So next step, final step, now we are going to find the heat transfer. We know the equation, that is Q is equal to neta into H into surface area into delta. They are simply HA into delta. Fin means an efficiency is added. Q is equal to efficiency of the fin into its convection, that is HA into delta. By substituting the efficiency as 91% and heat transfer coefficient 130 and surface area, that is 5.62, into its temperature difference, that is Tb minus T infinity, we can find the heat transfer per fin. So heat transfer per fin is 95.9 watts. Thank you. We'll meet in the next class.